Hello everyone and welcome back to Knowledge on Ears. Today we're going to actually look at what electromagnetism is and how it works. And today's video is going to be divided into three parts. First, we're going to take a look at this electromagnet right here. Then we're going to look at the theory. And then lastly, we are going to look at a cool doorbell and how it operates using electromagnetism. So let's start. Take a look at this. This is actually a screw, and there is a bunch of copper coils around it. This is insulated copper, and you can see the green part, that's the insulation on the copper. So at the ends, I've actually scratched off the insulation so we can actually use it. So now, what I'm going to show you is that once I actually pass a current through this screw, it's going to be able to lift these paper clips using magnetism. So right now, if I check and I try to lift the paper clips, it doesn't work. There's no magnetism right now, so it's not working. Once I actually connect the battery and I pass the current, you're going to see that it does work. Take a look at that. It just got lifted up. So why does this even happen? Well, it's due to something known as electromagnetism, which is basically just the relationship between electricity and magnetism. What we just did was that we created a magnet using this, and by passing this electric current through it, we used electricity to generate a magnetic field around this. An electromagnet is basically just creating a magnet using an electric current. Now, let's get going. So, there is a very fundamentally important relationship between electricity and magnetism. And what that relationship is whenever we have a wire, any wire, and we pass current through this wire, that generates a magnetic field. So keep in mind, for the rest of the video, when I talk about current, I'm referring to conventional current. So once again, if current flows through a wire, that generates a magnetic field. So now, let's take a look at a straight wire only. When current passes through a straight wire, the magnetic field that's generated is always in circles around the wire. It revolves around it. And so we can actually find the direction of the current flow or the direction of the magnetic field using something known as the right-hand thumb rule. Say that this is our wire, this marker. And so if we know, we're using the right-hand thumb rule, this thumb represents the direction of the current flow, and my fingers represent the direction of the magnetic field. So if we know that current is flowing this way, and this is our wire, then we find out that the magnetic field is moving this way, in circles around the wire. In the other direction as well, if we know current is flowing this way, then we know that the magnetic field is moving that way around the wire. So that's how we can figure out the direction of current flow and magnetic field for a straight wire. But in our example that we looked at for our screw and the copper wire picking up the paper clips, we did not use a straight wire. We used a coiled wire. And there is actually a big difference between the two of them. So over here we have a solenoid. And a solenoid is basically just an electromagnet that has a coil of wire around an internal core. And in this case, the core can be the steel screw that we looked at earlier, iron, or it can even be air. So there's a lot of different things that could be the core. And we have a coil of wire around it. And the difference between a straight wire and a solenoid lies in the magnetic field that it creates. So we already know when we pass a current through any wire, that creates a magnetic field. But since a straight wire is straight and a solenoid has a coiled wire, the magnetic fields created are different. So we know that a straight wire has a circular magnetic field. And those circles, they don't have any magnetic poles. It's just circles. But for a solenoid, because of its coils, that creates a magnetic field with a north and south pole. And those poles actually allow us to pick up those paper clips. So this is an actual electromagnet. So we can use the right-hand thumb rule, another one, to actually figure out either the direction of current flow or where north is, the North Pole. So we use the same positioning, the fingers and the thumb, but they represent different things now. The thumb represents the North Pole, where the North Pole is, and the fingers represent the direction of the current flow. So say that this is our solenoid again, and we know, so let's say that this is the wire passing through it. So we know that the current flow is moving down, and we want to find out where the North Pole is. So if the current flow is moving down like that, then the North Pole must be to the right here, the North Pole. We can also figure out the current flow if we know where the North Pole is. So if we know the North Pole is here, then the current flow has to be this way, the other way. So we used the right-hand thumb rule for both of the scenarios for different cases. So as we have already discussed, we know there's a coil around this electromagnet. And in this doorbell, there is also a coil. But where is the screw? The screw in this case is this metal piston that moves up and down. It's a metal rod that acts as the screw in our traditional screw electromagnet. So in this doorbell, it works in the same principle as our electromagnet does. So when we send current into the coil, it obviously gives us an electromagnetic field. Then this piston moves down and it hits this metal plate over here, which produces that ding sound, that ding noise that we hear. So now, let's get back to the current. We still have to send current to this coil for the electromagnet to actually work, and that's why we have this transformer. This is connected to our home power. So this part is a primary part of our transformer, and it takes in the 120 volts and steps it down to only 16 volts. We obviously don't want too much voltage coming onto this doorbell because we would need a larger coil and it could overheat, it could burn. So very easily this could all turn into a fire hazard. So please don't try this at home unless you have the proper setup. So once we use the step down transformer and we get the 16 volts, this gets carried through this wire to this common terminal right here. There are 3 terminals on this doorbell: the rear terminal, front terminal, and common terminal. The rear terminal is if you're going to put the doorbell in your backyard or at the back door. And this front one is for your front door, obviously. So the common terminal is connected to the step down transformer over here. And this rear terminal or the front, you can pick any one of them, but the rear terminal is also connected to the step down transformer. But we have broken this connection there by using a switch, which is this doorbell button. Now, this switch is put in series in the circuit, which means that we have cut this circuit. The circuit is not completed, and it will only be completed and the current will only flow when we press this button. So let me give you a demonstration of how this works. Did you hear that? Did you hear that ding sound? And now, if we hold this button for too long, what can happen? Do you hear that buzzing sound? That's happening because we are completing the circuit for too long. That buzz means that the coil may start to overheat. So let me show you how this doorbell works once again. Ding, 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 ding. You hear that ding, ding, ding? That's how the doorbell works. It's really simple, so cool. So this is our doorbell. Thank you so much for listening. I hope you enjoyed this video. Bye!